Okay, EE, I have seen a couple of rounds of your reports, and I'm impressed with a lot of what I'm seeing, and I have some very specific insights here on how to make calculations in this class. So all calculations require labels on all numbers. Okay? If you don't put a label on a number, it doesn't count. And what that means is there's so many different qualities of things that we're talking about that you need to know, like what the labels are, how they work, etc. So I'm going to just do a quick example here with current, charge, and time. So current, you're going to see mainly in milliamps. Charge is going to be coulombs, and then time is going to be seconds or hours. So, as you hopefully know by now, the equation for current in terms of charge and time is this. If you, like we talked about in a bunch of classes. So, if we were to solve for the charge capacity of a battery, we would say something like this. If I had, let's say that my battery is running for, let's say, 7 hours, and let's say that the current out of my battery was 150 milliamps, okay? The charge out of the battery would be the current times the time, so it would be 150 milliamps times 7 hours. Now, you could write that as, whatever, 1,050 or whatever the product is of those two numbers. You could write that as milliampere hours, which is actually kind of a legitimate thing to do. On the other hand, if I ask you to write that in coulombs, you need to do the unit conversion, and you need to do the unit conversion in a way that makes it clear that you understand what each little thing is. So I'm gonna show you how to do that. I'm going to write the 150 milliamps as 0.15 amps, and an amp is a coulomb per second. Okay, and an hour is 3,600 seconds. So if this is the sort of train track method that you do like you learned in physics, you're going to see here that the seconds cancel, the hours cancel, and the remaining unit is coulombs. Okay, so this would end up being, whatever the product of these three numbers are, that's the number of coulombs. Okay, so it is not true that a milliampere hour is the same thing as a coulomb. You can check your work using an online unit converter like Google or anything like that, but I need to see all the labels in your calculations, and you're gonna find that this engineering teacher is pretty picky about labels and calculations. So make sure that you express them correctly and ask questions about them if you have them. So for the second calculation I wanted to talk to you about involves something called Ohm's Law. Ohm's Law is sort of the backbone of all basic electrical engineering, and it tells us the relationship between current, voltage, and resistance, where I is current, V is voltage, and R is resistance. And of course, the labels here are amps, volts, and our new one, which is ohms. The abbreviation, by the way, for ohms is the Greek capital omega. Looks like that. So, Ohm's law, like any three-variable system, can be used to solve for any one of these quantities in any. Let me say that again. You use Ohm's law arranged algebraically to solve for the thing that you need. Okay, and then let me just introduce you to the triangle approach. So if you make a triangle out of I, V, and R, you can say that the one that you cover right? So like, for instance, if I cover the V, it's equal to I times R. Okay, if I cover the I, it's equal to V divided by R. If I cover the R, it's equal to V divided by I. Okay, and in fact, in today's quick calculation, we're going to look at how to find the best value for a current limiting resistor with an LED. Let me say that again. We're going to try to use Ohm's law to find the best value for a current limiting resistor that you're going to use to protect your LED from blowing out. So let's say that we have a 9-volt battery, just like a regular battery that you would use in a electronic device. And then over here we've got a red LED. Okay, so I've got my long leg and my short leg for positive and negative, and then the LED, as you remember, bye honey, has it's got a threshold voltage, right? And it has a maximum current that if you exceed it, you'll blow it out, okay? And in fact, the max current here is the thing that we want to control, because the voltage can be a lot of different things, but if the current exceeds about 30 milliamps, you'll kill it. Now, how do you know what the max current should be for your LED? There's a couple of different ways. One is that you could look it up. And the other is you could actually destructively test. So you could set up an ammeter in your circuit, blow out an LED on purpose, take the reading of the current that killed it, and then make sure you don't exceed that. Okay, the other consideration for max current is that you want to be as efficient as possible. So you want to have as little current as possible and maintain a lit LED. In other words, you want to maintain the threshold voltage so that you run the system efficiently. Like, why use more current than you need? Because current is the thing that's going to drain the battery. Okay, so you've got 9 volts. Let's say that my threshold voltage for my red LED that we measured was 2 volts. And we have a 30 milliamp limit for our LED. So the question is, what do we put in here for resistor value to limit the current? And we're going to use the R is equal to V over I to find the threshold voltage. Excuse me, to find the value of the current limiting resistor. Okay, so here's how we do that. We say, I've got 9 volts out of the battery. I know I want to limit that to 30 milliamps. Well, what does that give me for a resistance? The 9 divided by 3 is 3, and then 9 divided by 0.3, which is the number of amps, is, 0.03 is 300 ohms. So that's, you could just do this with a calculator, but it's 9 divided by 0.03 amps gives me 300 ohms. Okay, so the idea would be then to make this circuit with a protected LED, you would say, here's a battery, 9 volts. Here's a current limiting resistor of 300 ohms. Here's an LED. Here's a switch. And then the question is, what happens when you close the switch? Well, if you had an ammeter in this circuit, you would see that the reading on the ammeter never exceeds 30 milliamps, which will protect your LED. Okay? So that is how you find the value of a current limiting resistor, and it's important for you to recognize that the value of the current limiting resistor relates to the voltage that you're putting into your LED, so you need to know what that is. Okay, and that's going to be important when it comes to mission capacitor.